So for most of my, so far, short career, I've focused on the geochemistry of hotspots. So this famous image now from French Manowitz showing a low-velocity conduit beneath Pitcairn Island here. I still don't know why Pitcairn has such a giant plume beneath it. But I focus on the chemistry of lavas at hotspots, but my students they've dragged me kicking and screaming into backcrest basins and then now into subduction zones recently. So I've been forced to think a little bit about subduction zones, and the last 2 weeks I've been forced to think a lot about subduction zones, so we'll see what you guys think about my thoughts. So I think I can attribute this to Jessica Warren. 2004, 2005, geodynamics field trip to Hawaii. You can almost smell my eyebrows burning. So my students and I will go to remote islands and collect lavas and go to the labs, dissolve these rocks and separate out the elements of interest by column chromatography and analyze the isotopic ratios of these elements by mass spectrometry. And then we make up all sorts of stories about what those numbers mean. So why are radiogenic isotopes important for probing the composition of the Earth? Well, this is really fundamental. I want you guys to all walk away from this today and understand this concept. So radiogenic isotopes, so today I'm just going to show strontium, neodymium, and lead isotopes, and some trace element ratios are not changed when you melt the mantle. So the solid mantle and the melt in equilibrium with that solid have the same radiogenic isotopic composition. This is important because we can't drill to the mantle source that's melting. But we can get at the isotopic composition of this mantle source because these lavas upwell to the surface. We measure the isotopic composition of those lavas and we know the composition of the mantle source that melted to make those lavas. This is really important. It allows us to probe the composition of the melt source, of the mantle. Now, of course, those lavas can be modified during transit to the surface. Specifically, the isotopic compositions can be modified in continental settings by assimilation of crust, which is why I tend to focus on lavas erupted in oceanic settings, where assimilation is minimal, and we can look at pristine lavas, less evolved lavas, to minimize the effects of assimilation. But this statement holds in the oceanic mantle. So with this in mind, for over 50 years now, I'm not going to ask people if they know who this is.
Famous radiogenic isotope geochemist.
Well, he probably would have been a radiogenic isotope geochemist if he'd known about isotopes, but we could my field could certainly use somebody like this at this point. Anyway, so lead isotopes versus strontium isotopes, you don't really need to know what those mean right now, except to say that lavas erupted at various oceanic islands and mid-ocean ridge basalt localities have extensive lead isotope and strontium isotope variability, and this variability reflects the isotopic composition of the mantle source that melted to make those lavas. And for over 50 years now, since folks started measuring these two isotopic systems in lavas, we've been speculating about what this radiogenic isotopic variability means. And geochemists have been very good about making confusing acronyms that basically define N-member compositions. I'm not saying I embrace N-members necessarily, but they can be useful for understanding how extreme compositions might be formed in the mantle. So I've listed these different N-members here in order of, at least in my opinion, increasing uncertainty from top to bottom in terms of how the N-member formed. So lavas that mid-ocean ridge basalts are melts of a depleted mantle, DM reservoir, and this reservoir is almost certainly formed by long-term extraction of crust from the mantle over time, and as a result you end up with a mantle It's depleted in incompatible elements and involves radiogenic isotopic compositions here. Now this is enriched mantle 2, so EM2 going straight up here in the middle. I'm pretty convinced this is recycled continental crust. I'll try to convince you of that a little bit later. High mu, which is really high in the Greek symbol mu, which represents the uranium-lead ratio, high mu, is probably or has a component of recycled oceanic crust. The metasomatism has been argued, but that doesn't explain some important isotopic compositions that we've observed recently. And I have no idea what this is. I don't think anybody else does. Rick Carlson uses the word dog's breakfast to describe EM1, so I suggest we start calling it DB. Pelagic sediment, lower continental crust, subcontinental lithosphere, that's almost certainly not true. Metasomatism, I don't like that. Delaminated lower arc crust, CO2 fluxing the deep mantle domains, and there are more and more and more. Okay, and I really don't know. I think we can say now that EM1 is composed of material that was once at the surface, and I think I can convince you of that later, if you believe some recent results. Okay, so how do we evolve radiogenic isotopic differences? So this is SLIDR, so I want to back up and explain how we end up with radiogenic isotopic variability in the Earth's mantle. So this is a classic plot that we get in intro geochemistry courses. Hopefully you get this in intro geochemistry course. You would certainly get this in my intro geochemistry course. Strontium isotopes versus neodymium isotopes with depleted mantle up here, continental crust down here, and everything else in between. Well, almost everything else. There are some things that fall off this beautiful mantle array. We'll talk about that a little bit later. And the key with radiogenic isotopic variability is that you have decay. So in this case, on the x-axis, 87 strontium in the numerator increases over time as 87 rubidium decays, spits out an electron, a neutrino, and of course there's energy. The half-life here for 87 rubidium is 49 billion years. Okay, so to generate variability of 87, 86 strontium, the first thing you need to do is fractionate rubidium from strontium. So separate them into different reservoirs. And then you need to wait. You need to give the system time to evolve strontium isotopic composition, strontium isotopic variability. Okay, so how do we fractionate rubidium and strontium? Well, the key here in our planet is to melt the silicate mantle and generate reservoirs that have different rubidium-strontium ratios. So here's time, 4.5 billion years ago to today. We have some theoretical unmelted solid mantle that at some point in history melted. And when it melted, let's say it melted to 1% melt, so F is 1% or 0.01. The melt has a very high rubidium-strontium ratio compared to the mantle residue because rubidium prefers to go into the melt relative to strontium. Strontium also likes to go into the melt. It's an incompatible element. But rubidium likes to go into the melt much more so. And then there's this important effect of degree of melting. So if the melt is 3%, then or a larger degree of melt, then the rubidium-strontium ratio in the melt isn't as high, and the rubidium-strontium ratio in the residue is even lower. So there's an important effect here of the degree of melting. So for those students that want to model isotope evolution in the mantle, you can start with the simplest case, batch melting, where you look at the concentration of an element like rubidium in the liquids, and the concentration of that element, rubidium, in the original unmelted solid, C0, and that equals 1 over the degree of melting plus the partition coefficient defined here times 1, the quantity of 1 minus the degree of melting. So Cl over C0, the concentration in the liquid of that element of interest, like rubidium, divided by the concentration in the original unmelted solid. So F is the degree of melting. Values range from 0 to 1, so no melting to 100%. So let's look at rubidium. So concentration of rubidium in a liquid equal over C0 equals 1 over, well, let's fix let's fix D. So rubidium, let's fix D for rubidium. So if F is really small, Cl blows up to a big number. If F is really large, Cl goes to a smaller number. Now D is the partition coefficient, so this is just defined as the concentration of rubidium in the solid divided by the concentration of rubidium in the liquid. When D is less than 1, so that means the concentration in the liquid is higher than the concentration in the solid, the element is said to be incompatible. It's incompatible in the solid. When D is greater than 1, the element is compatible. So this is just really basic, simplest case, batch melting, and how you can fractionate rubidium from strontium, for example, in the Earth's mantle.
Matt?
Yeah.
In your figure there, isn't the mantle residue from 3%? Isn't the mantle residue from 3% higher than the mantle residue from 1%?
Shouldn't be, because you're pulling rubidium out like gangbusters, but not strontium. So the more you melt the mantle, the more you pull rubidium out. And this is just mass balance.
Okay.
All right, so I gave you the way to get at the melt, and it's just mass balance if you want to get at the residue. Anyway, I'm worried about getting hijacked there.
Yeah, go ahead.
Maybe because I'm sure you're going to hijack me later. Almost certainly. So in this case where the parent is more incompatible than daughter, so rubidium is the parent, it's more incompatible than the daughter, and the melt has higher rubidium-strontium ratio than mantle residue, then we can look at how the strontium isotopic composition over time is going to change. So on the day that the mantle melted and generated 2 reservoirs with different rubidium-strontium ratios, on that day, those 2 reservoirs had the same isotopic composition as the original unmelted mantle. So you have to give the system time to evolve radiogenic isotopic differences. So this is the 87 rubidium isotope over the 86 strontium isotope. That's just the rubidium-strontium ratio, right? So in order to change this isotopic composition over time, we take the 87, 86 strontium initials, so at the day of melting, plus this quantity, and that gives us our change in the strontium isotopic composition over time. Of course, when T equals 0, this term goes away, right? So what we measure today is just the initial. But the rubidium-strontium ratio, when the rubidium-strontium ratio is very high, and we give it time to generate 87 strontium, we end up with a very high 87, 86 strontium over time. When the 87 rubidium 86 strontium ratio is low, for example, in the mantle residue, the 87, 86 strontium ratio increases less rapidly. And of course, this depends on the degree of melting. So the degree of melting will then influence how the 87, 86 strontium ratio changes over time. And this is the case where the parent is less compatible than the daughter. So the samarium-neodymium system. So here's parents more incompatible than the daughter. Here the parent is less incompatible than the daughter. So samarium, the partition coefficient for samarium is greater than the partition coefficient for neodymium. Neodymium is more incompatible than samarium. So the mantle residue actually has a higher samarium-neodymium ratio. The parent-daughter ratio is higher in the mantle residue than in the melt. So as a result, the mantle residue, it grows higher, 143, 144 over time compared to the melt, right? There's the rubidium-strontium case, samarium-neodymium. But then there's another issue. So here's comparing strontium and neodymium isotopes. The other issue is that we don't know exactly when these different mantle reservoirs melt necessarily. So the timing of melting and the degree of melting can then influence the final 87, 86 strontium ratio that you measure. So mantle melts, which become crust, have high 87, 86 strontium and low 143, 144 neodymium, and mantle residues have low 87, 86 strontium and high 143, 144 neodymium. So this, when we look at isotopic systems like this, these are often under constraint because we don't know the timing of mantle melting, we don't know the number of times that the reservoir we're looking at was melted, we don't know the degree of melting or the melt model. We don't necessarily know the mantle composition that melted, depleted, primitive, or enriched, all right? So when we look at the isotopic composition of a basalt that's erupted at the surface today, it could potentially have a very complicated history. Geochemists will often simplify this and say that that reservoir melted once from primitive mantle 2 billion years ago. But the truth is, we rarely have that kind of constraint. Okay, so there's a lot of radiogenic isotope systems that you can choose. The key thing here is that what you need to know when you look at a radiogenic isotope system, so here's a parent nuclide and here's a daughter nuclide, and the tracer, if you want to make a prediction about how the isotopic composition of that system will change, you just need to know how the parent and daughter partition with respect to each other. So rubidium will partition into the melt, the parent, the daughter strontium partitions to the melt, but less successfully. Whereas the samarium-neodymium system, the relative partitioning is reversed. So neodymium prefers, the daughter prefers to partition to the melt relative to samarium. So that's all you need to understand when you're looking at these other radiogenic isotope systems. You want to understand how the uranium-lead system, how different mantle reservoirs will evolve with time. You just need to know whether or not uranium or lead is more incompatible. Okay, so here's this tricky thing that geochemists love to show geophysicists to confuse them. This spider diagram. And if you ever want to ask an intelligent question about a spider diagram, that's right, this is really funny. You look at the anomalies. So here, the elements in the spider diagram are organized in terms of relative compatibility. So in this case, we're only showing incompatible elements, the elements that prefer to go into the crust relative to the mantle, less incompatible elements over here, more incompatible elements on this side. And the concentration of a particular element in a rock is divided by the concentration of that element in primitive mantle. It can be something else. It can be mid-ocean ridge basalt, whatever you want. In this case, it's primitive mantle. So all the concentrations are normalized in this plot relative to primitive mantle. So where would primitive mantle plot? If we plotted primitive mantle in this diagram? At 1. So primitive mantle plots right here. So here's depleted Moore mantle that melts to make Moore. The depleted Moore mantle is depleted in the most incompatible elements relative to primitive mantle. And continental crust is enriched in the most incompatible elements relative to primitive mantle. So this is just depletion and enrichment. So when I talk about depletion and enrichment, that's what I'm referring to. Now when we look at these spiderograms, we expect smooth patterns because we've organized these elements in terms of their relative compatibility during peridotite mantle melting, but we see anomalies that stick out. Continental crust is really depleted in niobium and tantalum relative to elements of similar compatibility. So you have these negative niobium and tantalum anomalies and positive lead anomalies and negative titanium anomalies. And these are signature fingerprints for continental crust. Depletions and these 3 high field strength elements and enrichments in lead. So a geochemist in the audience or a geophysicist in the audience might say, why do we have depletions in niobium and tantalum in continental crust, right? You focus on the anomalies because some weird process in the past generated that anomaly, and then you've asked an intelligent question the geochemist can't really answer. Focus on the anomalies, and those will help you understand the processes responsible for generating this reservoir. Okay, so we're in the habit of putting up heads of famous scientists. I tried to go grayscale, but you know, it was a late night last night. So
one of them is black and the other one is white?
no. So by looking at the isotopic compositions of lavas erupted at the Earth's surface, we know the Earth's interior is heterogeneous. So, and subduction zones play a critical role in this process. So mantle melting and crustal formation extract incompatible elements from the mantle and create depleted domains in the mantle, like the depleted mantle sampled by mid-ocean ridge basalts. These reservoirs, oceanic crust and continental crust, are injected back into the mantle at subduction zones. So you're injecting trace element enriched reservoirs into the mantle. So you end up over time with a mantle that is this messy concoction of depleted reservoirs juxtaposed with geochemically enriched crustal reservoirs. And then we think these geochemically enriched reservoirs, these subducted crustal reservoirs, are returned back to the surface in mantle upwellings. And these two fellows had a pair of papers in 1982 arguing that subduction of sediment was important for driving the isotopic variability of the mantle, and subducted oceanic crust was also important for driving the isotopic composition of the mantle. And I think it's, well, we'll talk about this later, but it seems like a lot of sediment enters the Earth's mantle at trenches. We need to talk about how much sediment actually makes it into the convecting mantle. But if you take some number like 1 cubic kilometer per year over the last 3 billion years, and you can argue about this, of course, and that's the mass of Africa and South America in the Earth's mantle. Alternatively, you can look at oceanic crust injection into the mantle. So 20 cubic kilometers of oceanic crust is made at ridges every year, so 20 cubic kilometers ought to be going down in trenches every year. That's 5% of the mantle's mass in 3 billion years, assuming it's a uniformitarian sort of approach. Okay, so let's dig into the first concept. The first concept is sediment subduction to the mantle. So what sorts of constraints do we have? Well, Terry very nicely sent me a short article she wrote for the Encyclopedia of Geochemistry. And the reason I copied this was to impress upon you how simple sediments are. Good, all right, you're laughing. All right, kind of. I look at this and I almost want to give up. I'll be honest. This is terrifying to me. It's not, and we talk about a sediment going into the mantle, and we model that and how it might get modified in subduction zones, and then what might actually go into the mantle, and then we use rubidium, strontium, samarium, neodymium systematics to predict what ought to be coming up in hotspots. But then Terry throws this at me and reminds me that, well, actually, it's not a sediment. It's a whole range of possible compositions. Today, I mean, we might be closing in on a composition for sediment today, GLOS 2, right? But what about sediment 2 billion years ago? Well, we'll get to this later. You missed one thing here, Terry. This is really important. So I did this search on the 4th of July, unfortunately, but the kitchen sink. Okay, so you can almost see the end member, kitchen sink, will be plotted up here. But what really is striking to me, so this is Planck and Langmuir in 1993, is that what goes into subduction zones roughly is what comes out at the arc. I would never have attempted this myself in, say, 1992 if I weren't a freshman in high school. But I simply can't believe this works, right? This tells us that there are some important systematics governing the composition of sediments that come out of arcs, and they can be related to what's going into the mantle at arcs. So this gives me some sort of hope that we may then be able to deconvolve what goes past the arc into the deeper convecting mantle. So fluxes of sediments into subduction zones yield outputs at the arc that are systematic. And the same for this ratio, the thorium over lanthanum ratio of sediment going into the subduction zone yields a thorium over lanthanum, the sediment coming out on the arc. So what goes in really comes out. I mean, I'm still boggled that it boggles my mind that this works, but it does. And of course, so this paper in 1993, the last sentence of the paper is, although such recycling plays an important role in arc volcanism, so referring to sediment subduction, a larger fraction of subducted sediment may continue to descend with the plate into the deeper mantle. So whatever didn't come back out in the arc, and this is what I really would like to constrain, ends up going into the deeper mantle. And this is really something that I've been struggling with for 15 years, and I feel like I'm circling and sniffing around this problem of what's going into the mantle, and I'm not really sure how to bite it. Okay, so I'm going to suggest some possible ways forward in just a little bit. Now, how much sediment goes into the mantle at subduction zone? So I'm recycling this recycling slide from Brad Hacker's CIDR talk last year, and there are a whole range of possible values for the amount of continental crust going into the Earth's mantle today. Values ranging from going very close to 0 to values of nearly 5 cubic kilometers per year. So this is Peter Clift et al. In 2009, exploring the crustal production and crustal destruction over time. I encourage you to look at this. It gives you a sense of the upper limit, or definitely the upper range for the amount of sediment that might be going to the mantle. But this injection of heterogeneous sediments into the mantle is a really important process. And I think we're looking at a range of possibilities still. I wish and I'm hoping that we can better lock down these estimates for injection. But this is something, again, I'll get to in a little bit. Okay, so what if we get sediment into the convecting mantle? How do we get that sediment to continue descending? So there's a really neat paper I saw in 2009, Wu Fei et al., looking at how experimentally what happens to the density of sediment as sediment descends into the mantle. So here, Prem is shown, so density as you go with greater pressure, and the composition of, or the sediment that they're looking at, its density is described as a function of temperature with these 3 different lines. And the takeaway message here is between 8 and 9 GPa, so say about 250 kilometers, bulk continental crust compositions. So silicic compositions become denser than Prem, and therefore will continue descending into the mantle. Well, one thing you'll notice here is that the prediction is that the sediment will then pond at 660 and won't continue deeper, right? You're dealing with perovskite stability here, and this sediment is likely going to be less dense. So sediment, this is something, I'm looking at this paper again and wondering how we get sediment into the deeper mantle. That's a different talk. But the cool thing here is that I showed this paper to Brad Hacker, and he said, yeah, we never see materials come back up at ultra high pressure terrains that have pressures higher than this. So it's really nice to see this experimental constraint agreeing with field observation. So if you can get continental crust or sediments derived from continental crust to this deeper than about 8 to 9 GPa, it's going to keep going down, at least to 660. So do we see it again? I think we do. I mean, we have at least one example. We have a couple of examples. One extreme example from the Samoan hotspot. Not my favorite hotspot, Peter, but definitely a useful place to go. They have one beer and it comes in 2 sizes. So neodymium isotopes versus strontium isotopes. So this is the global ocean island basalt array right here, looking at the various M members, EM1, high mu, and mid-ocean ridge basalts or melts of the depleted mantle. And this is the Samoan hotspot extending down into crazy radiogenic isotope space. And we had a cruise in 2005 where we pulled up these rocks. It was within a year that we knew what their isotopic compositions were. And well, these compositions are extending clearly into the upper continental crust range. Now, Remember this spidergram I showed you guys earlier that showed continental crust? And there were some clear anomalies in the spider diagram. So niobium and tantalum depletion, titanium depletion, lead enrichment. So again, it's the same order of elements, so less incompatible to more incompatible. So really prefers to be in the melt here. The samples, their concentrations are all divided by the concentration in primitive mantle, and the black diamonds here describe the upper continental crust composition. So again, titanium depletion, lead enrichment, niobium and tantalum depletion. So if there's really a continental crust signature of some kind being contributed to these hotspot lavas, we ought to see these same patterns, these trademark patterns for sediment in the basalts, and we start to see these signatures show up in the most enriched lava, the red squares. So you see niobium and tantalum depletion, titanium depletion, and lead. It's not crazy enriched, but contrast that with other ocean island basalts in Morb, where you have strong lead depletion. So you're actually no longer depleted in lead. You're actually starting to show hints of a lead enrichment. So we use key trace element ratios to try to quantify these enrichments and depletions. So for example, cerium lead. Lead is ever so slightly enriched in this lava relative to elements of similar compatibility like cerium. So we plot the cerium-lead ratio. So cerium over lead, right here, the cerium over lead ratio. In continental crust, cerium over lead ratio is low because lead is so enriched. So continental crust has very low ratios out here. So if we're seeing some continental crust in these lavas, we're going to predict that we have higher 8786 strontium paired with lower cerium over lead ratios, approaching continental crustal values, and that's what we see in these lavas as we're going out towards these radiogenic isotopic compositions, high 8786, we're seeing lower and lower cerium lead ratios. So very characteristic of upper continental crust, or sediments, more likely sediments derived from upper continental crust. We can do the same tricks with niobium. So this is just quantifying the niobium anomaly, so whether or not niobium is enriched or depleted relative to nearby elements on the spidergram. So here's the spidergram here, here's niobium and tantalum right here. They are depleted relative to elements of similar compatibility like thorium here and lanthanum here. So if you were to draw an imaginary line between thorium and lanthanum, that's where you'd expect niobium and tantalum to be. That's what niobium star is. It's just what you expect niobium and tantalum to be if there were no anomaly, but you have depletions in niobium and tantalum, so this is really the normalized concentrations of niobium relative to what you'd predict. So if niobium is depleted, like in upper continental crust, you have values that are less than 1. Upper continental crust has very low niobium values relative to what you would predict based on the bracketing elements here. And so as 8786 strontium increases in these lavas towards upper continental crust values, we're seeing the niobium depletion become more and more enhanced. So we're looking at agreement between trace elements and radiogenic isotopes that really argue for some sediment composition that's gone into the mantle and has been brought up in this hotspot at Samoa. So what about recycling of oceanic crust? Well, this is also, I'm trying to avoid using the word complicated because it annoys some people in the audience, but it's complex. So, Terry, I'd appreciate if you'd send me a list of appropriate substitute words. So this gives you a sense for the range of trace element compositions that we see in fresh mid-ocean basalt in a narrow segment or a narrow portion of the mid-Atlantic ridge between 40 south and 55 south. And we're seeing over a magnitude of variability in the most incompatible elements, rubidium and barium. Fresh mid-ocean ridge basalt. So this represents some combination of mantle-source variability and melting processes that would fractionate these trace elements. But the key here is that this is what you end up with in a mid-ocean ridge basalt. Now, when we think about subducting a mid-ocean ridge basalt into the mantle, it's tempting to take one composition, pristine, take a pristine morb and stuff it into a subduction zone and model how its radiogenic isotopic composition will vary over time. But the truth is we have enormous variability in this really small portion of the mid-Atlantic ridge. This nowhere near captures the global variability. I'm just giving you a hint of some of the variability that exists in ridges. So before we try to understand what's going into trenches, we need to get a better sense for the variability of compositions that's going into trenches. And it's worse than that. So this is a nice paper that provides new data and compares this with pre-existing data for trace element compositions in altered oceanic crust. So as oceanic crust sits on the ocean floor for tens of millions of years, in this case up to 170 million years, that oceanic crust interacts with seawater, and that changes the composition of the oceanic crust in very predictable ways. First, alkali elements, so rubidium, cesium, potassium, and lithium. So rubidium, cesium, potassium, and lithium are all enriched in these altered oceanic crust compositions relative to what's being plotted there. Not primitive mantle. We're making a special comparison here with fresh mid-ocean ridge basalt. We want to get a sense for how altered oceanic crust compositions evolve by interaction with seawater with respect to fresh mid-ocean ridge basalt. Also, there's an enrichment in uranium right here, which ends up making really complicated evolutionary pathways for lead isotopic compositions in mid-ocean ridge basalt as it alters. Now, I think it's also important to mention that there are a number of elements that aren't changed a lot during these alteration processes. So the high field strength elements, niobium, tantalum, hafnium, zirconium, titanium, you can pick them out here. Here's a couple, niobium and tantalum right here, titanium here. And the rare earth elements, so lanthanum, cesium, praseodymium, neodymium, samarium, and so forth, right? These are little modified by interaction with seawater. So not only do we have highly heterogeneous oceanic crust being formed at the ridge, but we also have crust being modified by interaction with seawater over time before it enters the trench. Yeah?
The fresh one has so much variability. Which one is preference?
Which one it has so much variability, which one is the reference? So at least for the case of 801, so the data that were published in this particular paper, the fresh composition consisted of glasses that were identified in the core. Is this right, Terry? So there were.
And they were normal or depleted or fresh glasses. So this is with respect to that specific composition.
Now, this is something that continues to boggle my mind. Is you look at.
170 million year old glass.
And yes, thank you, Terry. It boggles my mind, and it's interspersed with incredibly altered basalt. I don't know how this happens. Okay.
Another question.
Yeah.
So is the fact that most of the elements plot just a little bit less than one an indication of there's so much of these alkalis, or is it something that's off of not on the diagram that's actually changing the overall balance? I mean, why are they all a little less than one?
It's water and CO2, which are not on the diagram, sorry. So there's enough water and CO2 to dilute everything else a little bit.
Yeah, Terry and I agreed up front that she would address that specific question. Yeah, Jeff, what was that, $5 or $10? Just kidding. No, I've been giving all those to Torsten, so you have to fight Torsten for those. So, okay, so we're dealing with highly heterogeneous oceanic crust, morb crust, that is variably altered in predictable ways. And then we stick that altered oceanic crust into a subduction zone, and we want to understand what happens to those crustal compositions as the crust undergoes a series of dehydration, metamorphic reactions, and as the crust heats up as it goes into the mantle. So this is a really amazing paper. This is 12 years old now, and I'm still trying to wrap my mind around this paper. It shows, it makes predictions about what happens, at least experimentally, what happens to basaltic eclogite. I'm trying not to say eclogite. Glenn Gaetani has influenced me in this way, and everybody snickers whenever I say eclogite. You take a basaltic eclogite composition, and at different temperatures, at 4 GPa, right, so 120 kilometers roughly, you look at how these trace elements partition between a fluid and the coexisting solid. And weird things happen. Well, people like to think of lanthanum and cerium being relatively immobile. Niobium and tantalum being relatively immobile in subduction systems, but in fact, at high enough temperatures, these rare earths and high field strength elements become pretty mobile. Now, this was sort of shocking for me. And as you go to higher pressures and temperatures, you're no longer dealing with aqueous fluids or hydrous melts. You're now in the supercritical fluid realm. And even more bizarre things happen. Even at low temperatures, at 800 degrees Celsius, you're starting to see lanthanum and cerium and neodymium and samarium mobilize into the fluid. Well, geochemists like to think of these as relatively immobile elements. But at low temperatures, at 6 GPa, in the presence of supercritical fluids, these light rare earth elements are moving all over the place. Niobium and tantalum are starting to show hints of mobility, even at low temperatures. As you pump the temperature up, the supercritical fluid is starting to host relatively large quantities of high field strength elements. Now, this was difficult for me to incorporate into my thinking at first, because we like to think of certain elements as being fixed in the slab. And that allows us to think about fluxes of other elements out of the slab with respect to these fixed elements. But then this told me that all sorts of crazy things are going on in this slab, and even elements that we thought were fixed may be potentially mobile.
Hey, Matt?
Yeah. Terry didn't agree to answer this question, so I'm on my own.
I think it's a pretty simple one. In these kinds of experiments, are the fluids emplaced with some particular high volume, or are they evolving naturally through the experiment?
So this goes beyond my expertise into the expertise realm of Christy Till.
Can you repeat the question?
So I guess I mean, yeah. In these kinds of experiments at these pressures and temperatures where they're talking about supercritical liquids, are they emplacing something that is a fluid and then thinking about the interaction between the solid and that, or are they creating, is it a melting process basically, and then they're looking at the process of melting?
Right. So the idea is that above the second critical endpoint, the solidus no longer exists. So there is no longer a boundary that represents melting. We only have aqueous fluid with, properties of a melt mixture and the solid. So there's not such a distinct, clear point at which we go from not having that to having it. So basically the inference would be that if you had aqueous fluids at lower pressures, you would have this substance at higher pressures. And it behaves like some combination of a melt and a fluid that we don't fully have a grasp on its material properties at these pressures, but it would be a much better carrier of a lot of these things that we think of as being relatively immobile at lower pressures. Probably just confused you more, but.
Now, what I want you to tell me is if you can see this niobium and tantalum in your images, your seismic images. That's the key for me.
Worry about finding the supercritical fluid first.
Yeah, to answer like how they did it, really you can just load basaltic powder and water. And in fact, there's a remarkable movie you can watch of, by in a hydrothermal diamond anvil cell where you can actually look at the experiment as it's going on. And so at low pressure, you can see that there's separately solid, liquid, vapor. And then you go to high pressure and the thing becomes one phase, a solid plus one phase. So it's quite remarkable. And this just happens with starting with a liquid and solid.
There is some debate about exactly where it happens, but it happens.
Remember the salt, sediment, peritite, and that's debated.
Yeah, what is the approximate pressures? Because I've heard
4, 5, 6 GPa,
Because it-
depending on what it is. So albite is like it too. Right. That's the one you can see, beautiful albite liquid. Right. Something like albite might be 2 GPa, so 60 kilometers depth. But the basalt or peritite supercritical point is kind of debated and could be 4 to 6 GPa, I think. So pretty deep.
Yeah, I think there's one estimate that's between 3.5 and 4 GPa, another that's at 6.
So these compositions were recovered from the quench, is that the idea? When they analyze these compositions afterwards and look at what's there and hope that whatever there is.
Ask Christy. I'm not the experimentalist here. I absorb the implications.
Yes.
They literally froze these.
Yeah, they froze them on a cryoscopic stage.
Yeah, and then lasered them.
Yeah.
They're pretty great experiments.
Christy, you have a question over on the other side.
Are the open symbols between titanium and hafnium important? If you don't want to answer that, that's
I'm looking for titanium. So here's titanium. You looking over here?
yeah. Each one of the symbols are colored for all of the elements, but then there are these additional open symbols for sort of that central portion.
Okay. I can't answer that
I'm gonna
question
guess
right
the
now.
answer's no.
I can't answer that question right now. Yeah. But I'll get back to you. Anybody else have a question for Terry? Okay, so remember, how do we think we generate high mu? Does anybody remember this? All right, it was probably sort of the middle of my confidence ranking in terms of how we make the different mantle reservoirs. How do we make high mu? Yeah. So high mu is high uranium over lead. So I look at what's happening to uranium and lead in these experiments, and generally it seems that lead is racing out of the solid into the fluid with respect to uranium, so that residual solid results in the residual solid has high uranium lead ratios. You can take a look at all the uranium leads at different temperatures and at different pressures, and this is generally true. So this is comforting, right? And in fact, Katie Kelly had a nice study looking at altered oceanic crust composition. So this is where that data from the 801 hole came from. And they were looking at the really high uranium-lead ratios, and they explored whether or not burning off the excess uranium that results from altered oceanic crust, burning off that excess uranium in the subduction zone, as well as getting rid of some of the lead in the subduction zone, can generate uranium, thorium, lead ratios that we see in oceanic island basalts today. And they were able to successfully generate these compositions. So that was, again, comforting. And so I feel like it's certainly possible that this residue of crust subduction, this residual slab that goes into the mantle, possesses the trace element abundances and ratios that can generate what we see in this high mu mantle reservoir. And there is a study a few years ago that looked at the sulfur isotopic composition of lavas that have the lead isotopic composition of high mu. So this high mu end member. And the sulfides in these lavas, in olivine phenocrysts, the sulfides trapped at magma chamber depths in olivines, had these bizarre sulfur, cap-33 sulfurs, so mass independently fractionated sulfur isotopic compositions. Anomalies going down to about minus 0.4 per mil. And the key observation here is that anomalies of mass independently fractionated 33 sulfur were only generated before about 2.4 billion years ago, and only at the Earth's surface. I'm not going to get into why that is, but all you need to know is that it ends up being an important tracer, not only for the timing of when that sulfur isotopic composition evolved, but also where it evolved, only at the surface. So when we see a sulfur isotopic composition coming up from below, that tells us that that composition was once at the surface, and it also tells us when. So Norm Sleep uses the term timestamp and certificate, that this composition was at the surface in deep time. So this gives me more confidence that the high mu reservoir was at the surface, and it can be modeled and went into the mantle, and it can be modeled as oceanic crust subduction. And then moving to my least favorite composition that we see coming out of the mantle, EM1, I think we might be able to say, based on results that came out recently from a French group, that EM1 is also sampling a reservoir that was once at the Earth's surface. So I'm not sure I can say much more about EM1 beyond that it was once at the Earth's surface. So they identified in Pitcairn lavas, sulfides in Pitcairn lavas, very large, much larger than the anomalies identified here, very large cap delta 33 sulfur isotope anomalies, minus 0.8 per mil. So remarkably large magnitude sulfur isotopic anomalies. Again, these anomalies were only generated in the Archean at the Earth's surface. So I think now we can say that high mu and EM1, with some confidence, were at the Earth's surface 2.5 billion years ago or earlier. Yeah, really very excited about this particular result. Okay, so let's take stock. EM2 requires some sedimentary material derived from continental crust that was at the Earth's surface. We see really strong signatures for continental crust in lavas at the Smolin hotspot, Society's hotspot, So-So, and the Marquesas hotspot. High mu looks to be some kind of crustal composition that was at the shallow Earth more than 2.5 billion years ago, and EM1 seems to share similar characteristics. It was at the Earth's surface in the Archean. Okay, so we have a sense for what kinds of compositions have gone into the mantle in ancient subduction zones over geologic time, and they've been recycled into hotspots. So this is where I venture out of my comfort zone and I look at these crazy isotope plots. I promise this should be pretty much it for this particular lecture, but I want to convey a few important concepts here. So this is a zoomed out image. This is a zoomed image right here. This relatively narrow region of isotope space. Remember the mantle array, this negatively sloping array that we generate in strontium, neodymium isotope space? Well, the first thing I want you to note is that altered oceanic crust zips off to the right. It doesn't follow the mantle array. Why is this? Turns out this is a very useful feature for altered oceanic crust if we want to trace it in the arc and then later in deep mantle recycling, right? Because it's pulling off the mantle array in a really unique way. Why is this? Well, the strontium over neodymium ratio in seawater is like 1 million. So if you cycle seawater through oceanic crust, you're going to imprint the strontium isotopic composition on the altered oceanic crust without imprinting the neodymium isotopic composition. The second issue is, remember the alkalis are enriched in altered oceanic crust? Rubidium is an alkali, strontium isn't. So you end up with very, very high rubidium-strontium ratios in altered oceanic crust, sitting there for 100 million years, and you evolve very radiogenic strontium isotopic compositions. But there's no similar enrichment of samarium, right? Samarium and neodymium are both rare earths. So again, the neodymium isotopic composition doesn't change. So this is a really key, useful signature that I'm going to be using in the future. Right now, I'd like to use it to understand subduction zone processes. Second, this is just a sampling of some of the sediment heterogeneity that we see in the world's ocean basins. This is from Terry's Gloss 2 paper, so these represent individual drill core averages. These fall in the mantle array and go to exceptionally geochemically enriched compositions. The third thing to look at is the ocean island basalt array. So what we see at hotspots. So behind everything else, mid-ocean ridge basalts ocean island basalts go from here to here, this range, and then, right, remember Samoa sticks out in this direction. And it's approximately going to sedimentary composition. So this is also nice to see, right? In isotope space, we see sediments plotting on an extension of this array. And mid-ocean ridge basalts. Now, people like to say that mid-ocean ridge basalts are homogeneous. But in fact, you look at the database of mid-ocean ridge basalts, and you find that mid-ocean ridge basalts actually exhibit significant variability. That, you know, it's a fairly linear array, but it expands almost all the neodymium isotopic variability that we see at hotspots. On average, mid-ocean ridge basalts are geochemically depleted relative to OIBs, but they can be very heterogeneous in terms of their radiogenic isotopic compositions. I plot back arc basins here, global back arc basins. And then finally, I plot two different arc compositions from the arc variability. I plot the arc compositions that are provided in the global database of Turner and Langmuir, where they look at global oceanic arcs and global continental arcs. So continental arcs span a range here, and oceanic arcs span a range here. So the variability in oceanic arcs is significantly less than the variability in global continental arcs. We can talk about the reasons for that. One possibility is that continental arcs have been contaminated by continental crust, but there's a counter argument. Continental arcs are sitting next to continents, and so you have a lot of continental material spilling off into the trench, and that continental material is being recycled back up in the arc, so generating more variability than you would see in an oceanic arc where you don't have so much continental sediment input. Okay. All right, so let's zoom in on this little area here. So here are mid-ocean ridge basalts. So this is the full range of mid-ocean ridge basalts, so the white diamonds. We're seeing some sediments here. We're seeing altered oceanic crust. Here's the one little outlier. But altered oceanic crust is shooting off to the right. Back arc basins. And then this is oceanic arcs. And what is absolutely striking to me, right? I will admit, shamefully, I have never made a plot like this that includes the global database of oceanic arcs. And when I made this plot a few days ago, I thought I'd made a mistake, because oceanic arcs are actually really homogeneous. This is frightening to me. Just think about everything that we're dumping into oceanic arcs. We're dumping altered oceanic crust that has incredible strontium isotopic variability, sediments that have incredible isotopic variability, and what comes out of the arc is actually quite homogeneous. It has half the variability in strontium and neodymium isotopes that we see in MORBs. Okay, so I'm sure some people in the audience are really comfortable with this. I'm not. Terry, I'm hoping you chime in here, because I want to park here for a second. So where is the sediment and altered oceanic crust input into the arc? We're dumping all this material, altered oceanic crust and sediments, and this is the global range we see for oceanic arcs. This is really troubling for me. Where are we seeing these smoking gun signatures for sediment input and altered oceanic crust input? And people will say, we need to look at lead isotopes. If you want to see this, I have some slides, after the talk. Arcs are also abysmally homogeneous. We're dumping in all this highly heterogeneous material into the arc, and the arc is spitting out lavas that are twice as homogeneous as MORB. So arcs aren't seeing much of this altered oceanic crust and sediment, strontium and neodymium isotopic heterogeneity or lead isotopic heterogeneity. Yes?
Sorry, right here. Just a quick question, because yesterday we were talking about databases and sampling biases, and whether the coverage in those databases is good, or there's possibility that that could be playing a role in this.
Yeah. So there are a couple of things that happen. I mean, you start off with 700 lavas that have major elements and isotopes, because we need to filter these and trace elements. We need to filter the lavas that are really evolved, because evolved lavas sat in the magma chamber longer. They've had more. They've been able to interact with the walls of the magma chamber, altered oceanic crust for longer, and so we worry about crustal assimilation. So we get rid of those, the low MgO lavas, and also the lavas that have really positive or negative europium anomalies, which also gives you hints about their degrees of magma evolution, right? So in the end, you just have a few hundred lavas. But you're sampling at least 10 oceanic arcs, right? So I can give you the database. You can ask yourself, is this really representative? It might be it's as good as we have. The surprising aspect of this is the existing global database.
Well, it might be fun. In the tutorial yesterday, we gave the students a bootstrapping Excel sheet to handle, look at distribution of data and sample bias. So it might be a fun exercise for some people to take that and see what happens when we put it through that. And also just, I'm curious a little bit, it might be fun not to sort of derail into sort of what are all of these things, right? But we can imagine if there are things that are, depending on how they relate to the melting process, how that might affect whether or not they're seeing certain parts of the signature that, dry melts aren't going to see that kind of stuff, whereas wet melts are, and so that kind of stuff.
You know, there are a couple of options here. Yeah.
So the yellow dots are derived from all of 3 holes that have ever been drilled in the ocean crust at various ages. So bear that in mind. We know very little about the net effects of seafloor alteration on the ocean crust because it's so difficult to drill. Most ODP drilling stops the second they get to the ocean floor.
Unfortunately, yeah.
But also recognize those are individual samples that you've plotted. That's not the average 6 kilometers of crust. It's not even the average 500 where most of the alteration
We don't
is.
know what the 6
The
kilometers
average
are,
500
though, right?
is
So-
always 704, at least in those 3 holes we've drilled. So I don't think that variability exists at the scale at which fluids will be scavenging elements from large portions of this lab.
Yeah, so we need deeper cores, right? Right now, I think the deepest core here is 500 meters into the old crust. How deep does this alteration go?
Well, another thing that's worth thinking about there is that the holes that Terry was talking about were drilled in the ocean crust before it came to the bending region to go down the slab. So what actually goes down the subduction zone could actually be quite different from what is existing in the middle of the ocean.
So to clarify, that bending process is going to get fluids even deeper into the crust, which could potentially shift more of the altered oceanic crust in this ridiculously radiogenic strontium isotopic composition. So that's an important thing to do. It's not going to be old, though, so. It's not old, but seawater 7092, which is right there. Yeah.
Matt, if I understand right, the point you're trying to make is that your oceanic arcs show much less variability than mid-ocean ridges, and you're troubled or excited or some combination.
I'm both.
Isn't it simpler just to say...
Both. I mean, yeah, both. Troubled and excited. I mean, this is...
There's a lot of stuff that happens between melting and the surface, and I would have looked at that and said, well, the magma reservoirs are longer lived and larger below arcs than mid-ocean ridges, and so things become more homogenized. And so I'm kind of missing why you're excited.
Because we're not seeing these extremes at all. And maybe it's this homogenization process that you're talking about. But
Every cartoon we've seen for an arc shows various magma bodies sitting below the volcano. And they're big. They're cartoons, but things are not going directly from the mantle to the surface.
Can I ask the mass balance part of this question, right? If, because you have this sediment or altered crust going in, but another thing we could look at doing is playing around with the percentage that you're mixing in with the melt being generated from the mantle wedge and the different masses of melt from those two, and then this homogenization process that you have. And so how much melt or fluid would you have to have from that sedimentary component to really shift the isotopic composition if the bulk of your melt comes from the mantle wedge?
this is a great CIDR project.
Why don't you stay next week?
Okay.
Actually, I'm just going to interrupt you now to say that we have 20 minutes till the coffee break.
Okay. So just really quickly, so the really neat EM talk we saw yesterday, right? And the results from your thesis suggest maybe a lot of this sediment, maybe a lot of that sediment is simply being cycled up, right, before it goes into the deep arc. But there's a mass balance problem there, right? There's only so much sediment you can stuff into the shallow subduction zone. I'm trying to find a different way to do this, Michael, other than magma chamber homogenization. Maybe this radiogenic strontium, right, it's tied up in the alteration phases, and maybe burn that off in the shallow arc. Maybe those are the fluids that are coming out, and that's why we don't see I mean, there's a hint that some of these arc lavas are being pulled off right here, away from the Morbier towards the altered oceanic crust. So maybe we're seeing subtle hints of that. Anyway, moving on. So can we use modern day subduction zones to generate some of the isotopic heterogeneity that we see in the deeper mantle? So we have a sense for the diversity of materials that are going into subduction zones and processes that can operate on the sediments and oceanic crust in the subduction zone. But another question is then what remains of that subducted package to go into the deeper convecting mantle? So there have been several different approaches to get at this problem. And one that I like was a Porter and White paper that came out a few years ago. And they tried to model this process using constructed slab compositions and primitive arc lava compositions. So the idea here is they take a homogeneous oceanic crust composition. So it's 80% normal morb plus 20% altered oceanic crust. So they just fixed that ratio and picked an altered oceanic crust composition, mixed it all up, and then they added the sediments compositions that have been compiled outboard of each of these subduction zones. So all the variability you see here is because there are different sediment compositions outboard of each subduction zone. So that's the input in their model. Then they model the output of subduction zones by assuming that 100% of the material that comes off the slab goes into the arc. So you have input, you have output, you assume a simple melting model, and these represent the residual slab compositions. Now so this is what they argue in their paper is going into the deeper convecting mantle. So then, well, Bill White is an isotope geochemist, so you can guess what he wants to do with this composition, this trace element residue. What do we have here? We have rubidium, strontium, we have samarium and neodymium, we have uranium, thorium, and lead. So he takes this composition of these 8 compositions, and he starts at 1.8 billion years ago. So he makes a calculation for what depleted mantle or morb looked like 1.8 billion years ago. And he assigns these slab residue trace element compositions to this protolith that's 1.8 billion years old, and then he forward ages it to the present day. Do you generate compositions that we see in modern ocean island basalts and morbs? So remember, lead, strontium, neodymium. You've seen these 2 plots throughout the talk. High mu, DMM, EM1, EM2, high mu, DMM, EM1, EM2. And these 8 different arcs with this simple model don't generate the isotopic variability that we see in the modern mantle. It fails to generate high mu compositions. It fails to generate extreme EM1 and EM2 compositions. Okay, when I saw this paper and I read it, I was really excited. I thought they are going to have the answer. They're going to finally tell me what I thought I already knew. Instead, their conclusion is using some really simple assumptions in present-day subduction processes, as well as we know them. What's going into subduction zones today wouldn't generate the kinds of compositions that we observe coming out of the mantle hotspots. So, for me, this is this is really fundamentally important because I think that subduction zones are really guiding the isotopic evolution of the Earth's interior. And this is a really good attempt at trying to model the isotopic evolution of the Earth's interior with subduction zone processes, but it didn't work. And I feel like we still have a giant hole in our understanding for global geochemical cycles for the Earth's deep mantle. And I think the fundamental limitation is arc processes and deep time. So there are a bunch of, and I want to add to this list. So I'm going to park here for a second as well before I advance to ideas that might be future CITER projects. Well, one thing they didn't do is they didn't vary the timing of subduction. They used 1.8 billion year subduction only. So maybe, I think we know that, at least from sulfur isotope constraints, that some materials being recycled up to the surface are more than 2.4 billion years old. So vary the timing of subduction, but also vary the composition of the subducted Morb protolith. We know that Morb has an incredible diversity of trace element compositions, fresh Morb. Also, maybe allow the entire Morb column, or more than just 20% of the Morb column, to exhibit alteration features. They fix the amount of sediment that's going into the subduction zones. They fix the ratio of sediment to crust, but I think if you relax that constraint and allow the sediment to increase relative to the crust, then perhaps you can generate these more extreme EM compositions. I'm going to skip this because I don't know what to do with this. Right? Yesterday's talk, a great talk. Maybe I back away from this right now, unless you guys want to drag me into this mess. Porter and White keep the sediment and oceanic crust packaged together. But if we want to generate high mu, there's nothing enriched about high mu. And sediments are going to give you everything you need for enrichment. So if you can somehow decouple the sediment and the oceanic crust, I think you can generate high mu. And Kelly et al. Showed that you could, with oceanic crust, generate a high mu composition. They specifically didn't include sediment compositions in their modeling. What about we relax this assumption that everything coming off the slab is going into the arc? I mean, this is a mass balance assumption that Porter and White made. I think you can relax this and see what happens. But then there are a lot of uniformitarian assumptions that, this deals with deep time, and this ultimately is what, these will be the difficult issues to deal with when we move forward to understand the geochemical evolution of the mantle, because I think the way subduction zones operate today, not necessarily reflective of how subduction zones have operated in the past, or the material that's gone into subduction zones in the past. So oceanic crustal weathering. Well, let's go into the Archean. We're dealing with anoxic conditions. So how does oceanic crust weather in anoxic conditions? You're almost certainly not going to get this uranium enrichment that we see in altered oceanic crust. Pelagic sediment composition. So, okay, we're grappling with global sediment compositions today and converging on a composition, GLOS 2, which makes sense. It looks an awful lot like upper continental crust, which is predominantly what's weathering and spilling into the oceans to generate sediments. But what did pelagic sediment look like 1.8 billion years ago? Can we use pelagic sediments today to model processes 1.8 billion years ago in the same way when we know that erosion and weathering must have been different? Right? No vegetation on the continents. Before 2.5 billion years ago, no free oxygen in the atmosphere. So how did weathering and erosion transpire, and what kinds of sediments were generated in the oceans? The composition of oceanic arcs and continental crust. Oceanic crust and continental crust may very well have been different. going into deep time. And of course, the temporal change in the thermal state of the Earth, and that's going to affect what part of the slab melts, how it dehydrates, how much of the slab melts. So these are all issues that that I have been, like I said, circling and sniffing around for the last 15 years and trying to figure out a way forward. And Porter and White, I think, was a really good attempt, and I think this is a really important modeling effort that is sort of going to be a hobby of mine in the near future. And maybe many of you are saying, Matt, get a life, but this is important. So I don't know how much time we have right now.
You should wrap up.
Okay.
So, I mean, we started about 5 minutes late, so we have about 10 minutes left in this session, but I suspect that there are questions. People would like to ask.
Deer in the headlights, no. Yeah, so if I'm going to wrap up, where do I want to wrap up? No, here. So this is where hotspots and arcs interact. So this is a paper by Kai Hornley and others in 2008, and they looked at the Galapagos hotspot tract, this Cocos Ridge, subducting beneath Central America, and they looked at the composition of arc lavas moving up and down through Central America. So the key here is looking at arc lavas that are erupting above the Galapagos hotspot tract and the change in chemistry of arc lavas as you move north away from the Galapagos hotspot tract. And what they found is that the chemistry of lavas erupted directly above the Galapagos hotspot tract have signatures that are going to Galapagos-like compositions. So hotspot-like compositions, remember, enriched neodymium 143, 144 would be low values, so geochemically enriched, low 143, 144, showing up in the arc right where the Cocos Ridge is diving underneath Central America. And as you move north, that hotspot signature fades away. Same for lead isotope compositions. You have more radiogenic lead, similar to the Galapagos, and the arc lavas directly above the Cocos, and moving north, you're going to sort of background compositions that are not reflective of a hotspot. So they see northward dilution of this hotspot signature, and they combine this with a seismic study looking at the splitting measurements, so seismic anisotropy beneath the arc, and they found trench parallel splits that argued, and they use this to argue for trench parallel flow. That all that tells you is the flow can be north or south, but then they could use geochemistry to say, well, in fact, the flow is to the north, because it's to the north where you're seeing this Galapagos hotspot signature entrained into the arc and diluted. This is really neat. So seismology can give you a two-way vector, and then geochemistry can tell you which way is possibly the correct way. In this case, it was to the north. And I think this is potentially a really important opportunity to explore mantle flow around subduction zones. We have a case in the Tonga system where the Louisville hotspot tract has been sweeping to the south over the last 4 million years. The Louisville hotspot is incredibly isotopically homogeneous. And where the Louisville hotspot is intersecting with the arc, you're seeing Louisville hotspot-like isotopic signatures show up in the back arc basin and in the arc, not shown here. And what's remarkable to me is even though this the intersection of the hotspot with the trench has migrated to the south over the last 4 million years, it's almost like the signature of the hotspot going into the arc is just being quickly erased behind the intersection of the hotspot with the arc. I feel like this gives us some important constraint on mixing times or dilution times within the arc. This is, I imagine this sort of gradient having moved south over the last 4 million years as the intersection of the arc with the subduction zone has moved south over this time period. This is something that could potentially be a CIDR project. You could look at any number of hotspot intersections with arcs, and we see this dilution, right? This dilution away from the intersection of the hotspot track with the arc. We see it in Central America as you move north, which was used to argue for northward motion and dilution of the hotspot signature in the arc. We see the same signature here, the dilution. But then there's enormous potential to link geochemistry in the arc, so with existing seismic data sets. So Doug is probably going to tell me that data sets are not going to be appropriate in the Marianas for this, but Pierce et al. Put together beautiful geochemical maps of the Marianas Basin. And it would be great to then superimpose this geochemical variability that's seen across the arc with variability and seismic signatures within the arc. Or even better yet, expand this work, this is 2006, isn't it? I put 2005. Getting mantle potential temperatures, so relating the geochemistry of lavas erupted in the arc with seismic shear wave velocities beneath the arc. You can argue about what these temperatures are reflecting, but is this a trend that continues beyond just these 4 points? So we will almost certainly have more data to work with now in the last 11 years to relate the thermal structure of slabs from petrologic thermometers to the seismic structures that we see. So all sorts of opportunities to use existing data sets in a relatively short period of time here at CIDR to make advances in our knowledge of subduction zones. So, thank you.
Okay, so let's spend 5 minutes doing questions, and of course the first ones who should be asking questions are students and postdocs right now.
Silence. So if there are no questions for me, are there questions for Terry?
So you have a sense for, or at least based on the very few drill cores, of what altered crust might look like. Is there any way we can hypothesize what serpentinites would look like on those diagrams? And would that even
which
matter,
diagrams?
be important? Like looking at your isotope ratios when you were plotting how homogeneous
There?
Yeah.
I think serpentinites, well, Jessica is going to probably want to weigh in, but serpentinites have interacted with altered oceanic crust to such a degree that you can imagine a mixing line between a seawater composition. So seawater would plot, it's heterogeneous in neodymium, isotopic composition. So serpentinites follow a trend, well, better to do it here, follow a trend horizontally, and then there's a very sharp turn in the hyperbolic mixing trend that then goes down to seawater. And serpentinites follow that composition away from morb, following the seawater mixing trend towards seawater. And the most ridiculously altered abyssal prototypes are actually, they turn the corner and head down. Yeah.
Can I ask a follow-up then? Because, so one of the components you haven't mentioned is the mantle portion of the plate that is subducting. And that does have compositional heterogeneity as well, though it is overall more depleted than the crust. But whether you think that component is important, ultimately getting, if it's reappearing at the hotspots ever.
Oh, I think it's super important. in a lot of ways. I mean, the mantle lithosphere of the downgoing plate has been largely stripped of its most incompatible elements, right? It's also, large portions of it are refractory because you've melted it already.
But also some portions of it are enriched because you've stuck some melt in there that's never made it out. So they're also, you can get a lot of trace element.
That's right. You see some of this. You see some of this in abyssal peridotite, right? Yeah. So yeah, potentially. I mean, yeah. Some people like to argue that you have some melt. It doesn't escape the mantle lithosphere portion of the downgoing slab, and then you try to make assumptions about how much melt and what kind of melt is there. It's still stuck, and you age it in the mantle for a couple billion years, and you generate compositions, and you see if that's what you see at hotspots. Okay, so that's been done, and one difficulty there is the trace elements rarely match what you see in hotspot lavas. So that's a problem. On the other hand, you also have large depleted portions, right? In terms of major elements, you've extracted a significant portion of melt from the mantle lithosphere at ridges. And so large portions of this mantle lithosphere are potentially unmeltable, or they're highly refractory and maybe would not contribute melt to hotspots. I mean, I think of these as maybe being portions of refractory peridotite that almost serves to dilute the mantle, right? You have large volumes of depleted peridotite that have had much of their incompatible trace element complement stripped out, and they simply dilute the mantle over time. So.
I have the microphone. So going back to one of the last plots you showed about the hot spot and that sort of gradient back towards sort of the non-hotspot signature.
This one? Or
no.
This one?
That one, yeah. So the Louisville influence. Do you have any intuition or theory on whether that's the sort of trend back towards away from the Louisville hotspot signature is mixing into the mantle, or is that signature just sort of getting advected away?
Yeah, it might be simply advected away. And that's probably a better explanation, because I think mixing wouldn't be sufficiently fast on this, few million year time scale we're talking about. So I think advection is a great possibility. In fact, I'd love it if you explored that. Yeah. I mean, so flow is probably north to south here because rollback rates are going to be higher in the north than in the south, and so I expect material to be going around that slab edge and being pulled south. This toroidal flow it must be going to the south based on the higher rollback in the north relative to the south. So I'm expecting some north-south flow, but there's also going to be a ploidal flow component, and you're arguing that could be the component that is affecting the Louisville signature away.
I'm not arguing anything. I'm asking you.
That's a good idea. Yeah.
Okay, I think you had a question, and then we'll end.
This may be a very naive question, but how do you get fresh morb? I mean, pillow lavas are terribly altered, and then you have these wonderful videos of black smokers and such. I just don't understand, but I noticed pictures shown by both Sarah and Christy. Presumably these are dredged samples. They look pretty fresh.
I mean, a lot of hydrothermal alteration doesn't happen everywhere, right? It's hard to find the smokers sometimes. So there's a lot of areas of erupted morb where it's still fresh, and you pull up dredges with fresh pillow basalt, fresh glass.
Interact with seawater?
Well, not all pillow basalt interacts with seawater. I mean Matt's been on cruises where they've dredged pillow basalt, right? So you can maybe comment on this, but it's not that everything on the seafloor is pervasively altered.
So so these basalts come to they erupt at the seafloor, and they quench. I mean, you're going from 1250 centigrade to 0 very rapidly. They quench to glasses. You have nice glassy rims on the pillow basalts on the ocean floor. But there often is some kind of assimilation on the way to the surface, but we can identify the signatures for assimilation. So when there's assimilation, we can steer clear of it and be wary of making too many interpretations about mantle source. And the key signatures for assimilation are those elements that are hyper-enriched in seawater. So for example, chlorine. So you look at chlorine over ratios of chlorine to elements that aren't enriched in seawater, like, for example, niobium. Very little niobium in seawater. So we look at chlorine-niobium ratios in basalts, in the pillow rims. And when we see very high chlorine-niobium ratios, it's basically a smoking gun for interaction with seawater. So yeah, it does happen. It's documented, and we have tools to make sure we avoid it. Is fractionate rubidium from strontium, so separate them into different reservoirs. And then you need to wait. You need to give the system time to evolve strontium isotopic composition, strontium isotopic variability. Okay, so how do we fractionate rubidium and strontium? Well, the key here in our planet is to melt the silicate mantle and generate reservoirs that have different rubidium-strontium ratios. So here's time, 4.5 billion years ago to today. We have some theoretical unmelted solid mantle that at some point in history melted. And when it melted, let's say it melted to 1% melt, so F is 1% or 0.01. The melt has a very high rubidium-strontium ratio compared to the mantle residue because rubidium prefers to go into the melt relative to strontium. Strontium also likes to go into the melt. It's an incompatible element. But rubidium likes to go into the melt much more so. And then there's this important effect. There's this important effect of degree of melting. So if the melt is 3%, then or a larger degree of melt, then the rubidium-strontium ratio in the melt isn't as high, and the rubidium-strontium ratio in the residue is even lower. So there's an important effect here of the degree of melting. So for those students that want to model isotope evolution in the mantle, you can start with the simplest case, batch melting, where you look at the concentration of an element like rubidium in the liquids, and the concentration of that element, rubidium, in the original unmelted solid, C0, and that equals 1 over the degree of melting plus isotope and strontium isotope variability. And this variability reflects the isotopic composition of the mantle source that melted to make those lavas. And for over 50 years now, since folks started measuring these two isotopic systems in lavas, we've been speculating about what this radiogenic isotopic variability means. And geochemists have been very good about making confusing acronyms that basically define end-member compositions. I'm not saying I embrace end-members necessarily, but they can be useful for understanding how extreme compositions might be formed in the mantle. So I've listed these different end-members here in order of, at least in my opinion, increasing uncertainty from top to bottom in terms of how the end member formed. So lavas that mid-ocean ridge basalts are melts of a depleted mantle, DM reservoir, and this reservoir is almost certainly formed by long-term extraction of crust from the mantle. Over time, and as a result, you end up with a mantle that's depleted in incompatible elements and evolves radiogenic isotopic compositions here. Now this is enriched mantle 2, so EM2 going straight up here in the middle. I'm pretty convinced this is recycled continental crust. I'll try to convince you of that a little bit later. High mu, which is really high in the Greek symbol mu, which represents the uranium-lead ratio, high mu, is probably or has a component of recycled oceanic crust. The metasomatism has been argued, but that isn't ratios. Are not changed when you melt the mantle. So the solid mantle and the melt in equilibrium with that solid have the same radiogenic isotopic composition. This is important because we can't drill to the mantle source that's melting. But we can get at the isotopic composition of this mantle source because these lavas upwell to the surface. We measure the isotopic composition of those lavas and we know the composition of the mantle source that melted to make those lavas. This is really important. It allows us to probe the composition of the melt source, of the mantle. Now, of course, those lavas can be modified during transit to the surface. Specifically, the isotopic compositions can be modified in continental settings by assimilation of crust, which is why I tend to focus on lavas erupted in oceanic settings, where assimilation is minimal, and we can look at pristine lavas, well, less evolved lavas, to minimize the effects of assimilation. But this statement holds in the oceanic mantle. So with this in mind, for over 50 years now, I'm not going to ask people if they know who this is.
Famous radiogenic isotope geochemist.
Well, he probably would have been a radiogenic isotope geochemist if he'd known about isotopes, but we could my field could certainly use somebody like this at this point. Anyway, so lead isotopes versus strontium isotopes, you don't really need to know what those mean right now, except to say that lavas erupted at various oceanic islands and mid-ocean ridge basalt localities have extensive lead. So for most of my, so far, short career, I've focused on the geochemistry of hotspots. So this famous image now from French from Manowitz showing a low-velocity conduit beneath Pitcairn Island here. I still don't know why Pitcairn has such a giant plume beneath it. But I focus on the chemistry of lavas at hotspots, but my students they've dragged me kicking and screaming into backcrest basins and then now into subduction zones recently. So I've been forced to think a little bit about subduction zones, and the last 2 weeks I've been forced to think a lot about subduction zones, so we'll see what you guys think about my thoughts. So I think I can attribute this to Jessica Warren. 2004, 2005, geodynamics field trip to Hawaii. You can almost smell my eyebrows burning. So my students and I will go to remote islands and collect lavas and go to the labs, dissolve these rocks and separate out the elements of interest by column chromatography and analyze the isotopic ratios of these elements by mass spectrometry. And then we make up all sorts of stories about what those numbers mean. So why are radiogenic isotopes important for probing the composition of the Earth? Well, this is really fundamental. I want you guys to all walk away from this today and understand this concept. So radiogenic isotopes, so today I'm just going to show strontium, neodymium, and lead isotopes. And some trace elements explain some important isotopic compositions that we've observed recently. And I have no idea what this is. I don't think anybody else does. Rick Carlson uses the word dog's breakfast to describe EM1, so I suggest we start calling it DB. Pelagic sediment, lower continental crust, subcontinental lithosphere, that's almost certainly not true. Metasomatism, I don't like that. Delaminated lower arc crust, CO2 fluxing the deep mantle domains, and there are more and more and more. Okay, and I really don't know. I think we can say now that EM1 is composed of material that was once at the surface, and I think I can convince you of that later, if you believe some recent results. Okay, so how do we evolve radiogenic isotopic differences? So this is SLIDR, so I want to back up and explain how we end up with radiogenic isotopic variability in the Earth's mantle. So this is a classic plot that we get in intro geochemistry courses. Hopefully you get this in intro geochemistry course. You would certainly get this in my intro geochemistry course. Strontium isotopes versus neodymium isotopes with depleted mantle up here, continental crust down here, and everything else in between. Well, almost everything else. There are some things that fall off this beautiful mantle array, We'll talk about that a little bit later. The key with radiogenic isotopic variability is that you have decay. So in this case, on the x-axis, 87 strontium in the numerator increases over time as 87 rubidium decays, spits out an electron, a neutrino, and of course there's energy. The half-life here for 87 rubidium is 49 billion years. Okay, so to generate variability of 87 86 strontium, the first thing you need to do